GR for kind introduction. Can you hear me?
Yes, we can hear. Yeah.
Yes, thank you. Okay.
Yes.
Yes, good morning, good evening, ladies and gentlemen. First of all, I would like to thank the organizers of this conference, especially GR, for inviting me as a plenary speaker. It is a great honor for me to deliver this talk, even though I feel a little bit odd talking to my laptop computer in the middle of the night here in Japan. Now, what I would like to talk today is about my research works I've been doing for a long time since I took a post in University of Tsukuba. My interest had reached to the field such as robotics. But recollecting my 25 years of research life, I've suddenly noticed that I was always fiddling with beam elements. In this lecture, I would like to talk about several finite element approaches to solve problems in structural dynamics, all using beam elements for numerical modeling. First, a brief outline of the YesIGot code incorporated with linear Timoshenko beam elements is introduced. This code provides higher computational efficiency than the conventional code in those problems with strong nonlinearities, including phenomena such as member fracture and elemental contact. Several results obtained by using this numerical code are shown in this lecture. Next, a torque cancelling system that stabilizes mechanical sway in quick motion robots is described. The TCS computes reaction moments generated by motors in robots by considering the precise dynamics of the whole system. The reaction moments can be computed using the parallel solution scheme of inverse dynamics, which handles the dynamics of complex robotic architectures by modeling them with Bernoulli-Euler beam elements. Some experimental results of torque cancelling are presented in this lecture. Now, first of all, let me explain about the YesIGot code. The key algorithm implemented in this code is called the YesIGot technique, which is a modified version of this adaptively shifted integration technique. This figure shows a linear Timoshenko beam element and its physical equivalent with a rigid body spring model. This cross mark represents the numerical integration point in the finite element model, and these two solid circles represent the rotational shear springs connecting these two rigid bars in the RBSM. In the RBSM, a plastic hinge is expressed by reducing the stiffness of the springs. And this equation shows a relation between the location of a numerical integration point and the plastic hinge, which is obtained by considering the equivalence conditions between the strain energy approximations of these two models. When a numerical integration point is located at the midpoint, a plastic hinge can be expressed in the middle of the element. Similarly, a plastic hinge at the left end can be expressed by shifting the numerical integration point to the right end and by reducing the stiffness of this element. Now, by using this relation, a precise location of a plastic hinge can be expressed and a highly accurate elastoplastic solutions can be obtained. However, limitation of one-point integration inaccuracy begins to emerge when applied to a model of a small number of elements, and accuracy falls drastically in elastic solutions. So we try to improve the accuracy in elastic range by simply changing the initial location of the numerical integration point. In the formally developed ASI technique, the initial location in elastic range is at the midpoint of each corresponding element. Instead, we place the numerical integration points of the two consecutive elements forming an elastically deformed member in such a way that stresses and strains are evaluated at the Gaussian integration points of the two element member. Gaussian integration points are known to be optimal for two-point integration, and accuracy in bending deformation is mathematically guaranteed. Now let me show you how it works in actual analysis. Some seismic response analysis of a simple space frame are performed for the estimation. These figures show the response obtained at the upper left corner of this frame. The number of elements shown in this figure indicate the element subdivision number per member. Because the plastic hinges are expressed only at the midpoints of the elements, the conventional FEM indicates a very slow convergence, and nearly 32 to 64 elements per member are needed to obtain the converged solutions. In contrast, the YesIGot code shows a very fast convergence. The converged solution is obtained with a minimum subdivision of 2 elements per member because the stress evaluation points in the elements are adaptively controlled in both the elastic and plastic ranges. From these results, it can be concluded that the 2-element subdivision per member is sufficient to acquire the overall behaviors of frame structures. Next, we performed a seismic response analysis of a 4-story steel building and obtained the result was verified by the one obtained by the eSimulator, a high-performance simulator developed in the National Research Institute for Earth Science and Disaster Resilience, NIED. These are the models constructed for the both codes. The eSimulator model has a very fine mesh which consists of over 5 million solid elements with 22 million degrees of freedom. On the other hand, the model for the YesIGot code consists of around 1,000 beam elements with just under 6,000 degrees of freedom. Now, please remember these members are subdivided with only 2 linear Timoshenko beam elements per member. The numerical results were validated by the experimental result obtained at the E-Defense NIED. The interstory drift angle obtained by the eSimulator, the red broken line in this figure, agrees well with that of the experimental result, the blue line, until approximately 7 seconds. However, the differences of the phase and the amplitude become larger in the region after 7 seconds, where the amplitude of the input ground motion decreases. The result obtained by the YesIGot code, the black line, on the other hand, shows good agreement with the experimental results for both the phase and the amplitude. Although the peak values near 6 seconds show smaller values, the behaviors in the other paths are well documented. These figures show the deformations and the distributions of the plastic region obtained by both codes at 6 seconds. The deformation is magnified 10 times, and the colors represent the distribution of the equivalent stress in the eSimulator model and the distribution of the yield function values in the YesIGot model. The plastic regions around connections are localized, and the positions of the plastic regions match in both results. I would also like to emphasize the performance of the YesIGot technique by comparing the computational times. The YesIGot technique can also be applied to those problems with member fracture. This figure shows the locations of the numerical integration points for each stage in the YesIGot technique. As mentioned, the numerical integration points in elastic range are placed at locations where those can express the stress evaluation points at appropriate locations for two-point integration. A plastic hinge is likely to occur before it develops a member fracture, and the plastic hinge is expressed by shifting the numerical integration point to the opposite end of the free plastic section. Accordingly, the numerical integration point of the adjacent element forming the same member is shifted back to its midpoint where it is appropriate for one-point integration. When fracture is judged to occur, the numerical integration point of the element is shifted back to its midpoint, and the stiffness is reduced to 0 to deactivate the element. Sectional forces exerting at the fracture section are released instantly at the next step after fracture has occurred, which is determined by using this fracture condition containing each strain value. For the elemental contact algorithm, let me show you this animation to let you get the image. Contact determination is done by examining the distance between two colliding elements using geometrical relations of 4 modes. Two elements are determined to be in contact if both of these angles are acute. Two elements are bound with a total of 4 gap elements as shown in this animation. Sectional forces are delivered through these gap elements to the connecting elements. The gap elements are automatically eliminated after some time of contact when the mean value of deformations of gap elements is decreased to a certain ratio. Two elements are determined to pass by if one of these angles are obtuse. We implemented these algorithms to a numerical code using the YesIGot technique and carried out various impact and collapse analysis of frame structures. Now let me show you some of the numerical examples. An aircraft impact analysis of the World Trade Center Tower 2 was carried out to investigate on the true cause of the WTC collapse. The numerical model was constructed based upon the information from the FEMA and NIST reports. Full models of the building and the Boeing 767 aircraft were constructed with linear motion beam elements. All structural members of the aircraft were assumed to have box-shaped cross-sections and the material properties of extra superduralumine. The initial velocity of the aircraft was set to 262 meters per second, and the total mass at the time of the impact was assumed to be around 140 tons. We applied the implicit scheme with numerical damping as a time integration scheme to avoid any numerical instabilities. Now these are the global view and the upper view of the tower during impact. The colors in the movie indicates the yield function values. The red color, for example, means that the sectional forces in the element have reached the yield condition. Fractured elements are deleted in these movies. Now, if we look at the result from a global view, we can see the stresses dynamically redistributing like a wave as soon as the aircraft cuts through the surface of the building. Now, this dynamic behavior is what we should investigate, since these kinds of high-rise buildings are not designed to withstand such dynamic transitions of stresses. From the upper view, we can see that both engines are detached from the aircraft soon after the main wings crashed into the surface. The left engine reduces its speed rapidly as it directly enters the core structure. The right engine, on the other hand, glances off the core structure and goes out of the northeast corner of the tower. This figure shows the transition of axial forces in one of the core columns, and the actual displacement at the site of every 10 stories from the ground floor to the top floor. Core columns are compressed constantly until the snout of the aircraft reaches the core structure, after which a wave due to impact and member fracture propagates in horizontal and vertical directions. At the lower levels, compression changes to tension immediately after the left engine hits the core structure and continue to vibrate with large amplitude. This core column at the 60th floor, for example, is heaved for 25 centimeters in 200 milliseconds as a result of this dynamic transition. This phenomena is what we call a Springback phenomena, which occurred due to rapid unloading in the core columns during the impact that might have caused the destruction of member joints. The next example is a fire-induced collapse analysis, which was carried out on a 30-story 7-span tower to determine the effect of the redundancy produced by outrigger truss systems on rooftops. The reduction of modulus of elasticity and yield strength due to elevated temperatures were taken into account. We carried out these 3 cases of fire patterns to see how the outrigger truss system helps elongating the collapse initiation time with its catenary action. Now these are the movies showing progressive collapse sequence for the 3 cases. I'm sure you can see how the shockwave propagates through the columns and moves faster than the fall of the upper structure. The shockwave seems to destroy the member joints on its way to the ground level. The fire patterns do not seem to affect the overall collapse behavior. However, the slanting modes are different and the clock's initiation times become faster or longer depending on the strength and the amount of the atrial trusses related to structural deficiency. Next, the numerical code is applied to a seismic pattern analysis of the Nouveau Leon buildings. A 14-story apartment consisted of 3 similar buildings connected with narrow expansion joints in which 2 out of the 3 collapsed completely during the 1985 Mexican earthquake. The building was in Mexico City, which was about 400 kilometers away from the epicenter. Now, this event is known to be the first big disaster humankind has ever experienced caused by a long period ground motion. We constructed a model of the 3 connecting buildings with a total length of 160 meters. As shown in this table, we set the natural period of the north building model to be 25% longer than the other periods by lowering the structural strength of the columns. The difference of the natural periods was actually observed in similar buildings built near the site caused by the damage from previous earthquakes. The EWNS and UD components of the SCT seismic wave shown in these figures were applied. The intensity period of the seismic wave was approximately 2 seconds because of the reclaimed soft soil of Mexico Valley, and it happened to be resonant with the buildings of this height. A collision first occurs between the north and the center buildings due to the difference of the natural periods, and the plastic region spreads through the beams and columns. The collapse of the center building is initiated because of the continuous collisions from both sides. Although the north building collapses a few seconds after the center, the south building withstands the collisions and does not collapse. We also performed a continuous analysis of a steel frame building subjected under seismic excitation, followed by an input of tsunami wave and collision with the debris. A numerical code using the stabilized FEM based upon the volume of fluid method, which indirectly expresses a free surface shape by function values, was adopted for the fluid analysis. A numerical model with a region of 240 meters in length, 180 meters in width, and 80 meters in height, as shown in these figures, was constructed. A tsunami evacuation building model was located near the center of the whole model. 2 types of buildings without any openings and with openings as shown in these figures was subdivided with finite element measures. This building with openings was actually designed for evacuation uses in this reference. The buildings were modeled as rigid bodies that allowed no deformation, and the openings were assumed to be located at the window parts. These models were all subdivided with tetrahedron elements with the distances between nodes fixed at approximately 50 centimeters under the waterline and around the building. The shape of the flow surface and the pressure distribution computed at the front of the building are shown in these movies. We can observe the inflow and propagation of tsunami wave and the impact to the front of the building. A complex free surface shape owing to amplification by reflected waves, for example, appears to be well simulated. The seawater flowing in and out of the openings can be observed in this movie for the model with openings. A wide area at the lower part of the buildings is highly pressurized in case of the model without openings, but the pressure is significantly reduced in case of the model with openings as seawater flows into the building. Next, the behavior of the building during seismic excitation is analyzed by using the YesIGot code. As you can see, comparatively large sectional forces appear in the building as it deforms largely at the first peak of the input wave and at the second. The residual and maximum interstory drift angles are shown in this figure on the right. The maximum interstory drift angle reached nearly 1/50th radian in 7th floor and nearly or over 1/100th at other floors. However, the residual interstory drift angle at all floors were very small. So it can be said that the damage caused by the seismic motion itself was very small. Next, a debris impact analysis was conducted after applying a tsunami wave force in the most severe condition. 6 container boxes were placed side by side at this location, 30 meters away from the front surface of the building. An initial velocity equivalent to the tsunami flow was given to the container boxes in the direction of the building to simulate the impact phenomena. This movie shows the behavior of the building owing to impact of the tsunami debris. The container boxes collide near the second and third floors, causing ultimate material failures to the columns and beams around the impact point. The shockwave rapidly propagating from the impact point can also be observed. The relative velocity between the debris and tsunami flow increases when the debris reduces its speed in front of the building. Then a much larger drag force is applied to the debris and thereby to the building itself. Member fractures initiate at the front columns of the first floor and propagate progressively to the inside. Finally, the building collapses and is washed away. Next example is a ceiling collapse analysis. This picture was taken inside a gymnasium a short time after the Great East Japan earthquake in 2011. You see how the plaster boards, which weigh about 10 kilograms each, fell and scattered all over the floor. We must prevent these phenomena from happening because these facilities are likely to be used as a shelter after earthquakes. The components of the ceilings at the backside are quite complicated, as you see here in this picture. These clips are small and delicate components, and they may be detached during repeated excitation. Once there's a local detachment of clips, a change in the load distribution may cause a chain reaction of detachments, which ends in a drop of plasterboards. Also, there are some reports which say that the detachments of hangers or failures of screws had caused the ceiling collapse. So there are various factors we have to assume. There are some preliminary tests done to see the actual strength of these components. For example, the opening of clips began at a tensile force of 0.4 kilonewtons and the opening of hangers at 2.8 kilonewtons. And for the screws connecting plasterboards to the ceiling joists, they are known to be shear damaged at a value of 0.3 kilonewtons. And the heads will become loose when 0.2 kilonewtons of tensile force is applied. We overestimated the strength of clips because they tend to slip under excitation and implemented these criteria to the analysis. This is a gymnasium model with the ceiling. Elastoplastic buckling of braces and hanging boards were taken into account by modeling them with a few more beam elements. A shake table test was performed by the E-Defense under an input weight of KNet Sendai 50% wave, and we compared the numerical result with the experiment. Now this is the numerical result. The clips near the rooftop began to lose due to the buckling of hanging boards caused by vertical excitation, which ends in drop of plasterboards in wide area, as you can see here. The computation time was about 100 hours using a standard personal computer. So you see that the acceleration and displacement response of the numerical model agreed well with the experimental results. Furthermore, the ceilings collapsed near the rooftop as in the experiment, It was confirmed that the additional forces exerting of the joint metals due to the buckling of suspended bolts and the vertical vibration of the ceilings caused by the eccentricity of hangers. As a result, the ceilings were damaged intensively near the rooftop. Next, I would like to show you a recent simulation on the behaviors of furniture during seismic excitation. Analyzed the motion behaviors of these furniture and validated with the experimental results. There were 5 furniture altogether, from very heavy cabinet of about 44 kilograms to a very light office chair with casters of about 6 kilograms. The location of center of gravity of each furniture was carefully measured beforehand. We measured the motion of each furniture by using a motion capture system as shown in this picture. 6 infrared cameras are arranged around the shake table to measure the position of luminous markers on each furniture. And this is an example of the obtained data. These are the finite element models of furniture on the shake table. All components were modeled with linear Timoshenko beam elements, and the center of gravity of each furniture was simulated by adjusting member densities. We did not use any finite elements for the walls and for the shake table floor, and the contact on the walls and floor were judged upon geometrical relations. To simulate various contact phenomena during seismic excitation, frictional contact between objects was considered using a sophisticated penalty method. This figure shows the subjected forces and the geometrical relations between 2 elements when they approach each other with a relative velocity. Penalty force in normal direction and frictional forces in tangential and normal directions are considered in this code. One of the features of the developed code is that it is easier compared to the distinct element method to select the contact parameters. We fix the penalty coefficients and dynamic friction coefficients based upon quite simple rules as shown here. First of all, we fix the penalty coefficient alpha as the weight of each furniture. We fix the dynamic friction coefficients as 80% values of each static friction coefficients, which were measured before the experiments on the shake table. And as for the coefficient related to damping, DC, we fix them as 120% values of the penalty coefficient alpha. We applied these rules throughout all the analysis. Now see how it works. I'm showing you the comparison of the values for the experimental results and the numerical results. The input seismic waves are different between the upper and lower rows. Now I'm sure you can see how the motions of each furniture are well simulated, particularly the rocking motion of the cabinets and the sliding motion of the furniture with casters are well simulated. You can also see the accuracy of the analysis in the comparison with the measured displacements. These displacements were measured at the top of the separated cabinet using the motion capture system. In various cases of seismic waves, the measured data for horizontal and vertical directions matched almost perfectly. Now, the next part of my talk is related to the robotics field. Let me explain about the torque cancelling system we've developed. This figure shows the concept of the TCS for the uniaxial case. Suppose a rotor is rotated by a motor with a specific torque. A reaction moment will occur around the rotating axis, which will make the whole body twist around this axis. To avoid this reaction moment from making the twist, we could generate a cancelling moment by another motor placed on the axis to supply a specific cancelling torque. Now please note that this cancelling torque is a perfect duplicate of this reaction moment. Now if the object in motion is an outboard rotor or cantilever beam as shown in this figure, the reaction moments will act around three-dimensional axis because the center of gravity of the overall body is at the offset position from the rotating axis. To cancel these moments, three systems, each set on each dimensional axis, should be placed. The accurate consideration of the dynamics and the calculation of input torque to the TCS are carried out by using the parallel solution scheme, which is developed based upon another finite element approach. In the parallel solution scheme of inverse dynamics, we use the incremental equation of motion as shown here. As you can see, it is written in the dimension of force. By applying the Newmark's beta method as a time integration scheme, the equation of motion is transformed into this equation, which gives the incremental nodal force vector. A target trajectory is given as an input, and nodal forces are obtained in parallel by calculating this global equation. Although the scheme requires incremental calculation, it has been confirmed in previous works that the calculation time in an actual control is suppressed to a practical value. This figure shows the nodal forces acting on the ith link in an n-link system. The joint torque tau ix required around x elemental axis on the ith link is determined by adding the moment generated by the nodal forces acting at the tip, the moment of inertia acting on this link, and the joint torque required around x elemental axis on the next link. By considering other components around the y and z axis and arranging them into global coordinates in a matrix form, the joint torque vector is expressed as this equation. The equation is completely separated into terms of different parameters, and each matrix has a clear physical meaning related to the modeled link system. The separation of the parameters makes the equation highly expansible and flexible, and so the scheme becomes applicable to complex link systems without difficulty. The member length matrix Ln, for example, contains components in the dimension of length which play roles in converting forces to torques. Now I would like to show you some of the experimental results. A simple rotor TCS experimental setup, as shown in these figures, was made to carry out a numerical estimation and some experiments for verification. In this setup, a rotor is driven by a gearless motor, and the prototype TCS is placed underneath with a rotation underneath exactly at the rotating axis of this rotor. The frame body is connected to the ground with a rotation-free pin joint, when an encoder attached to a non-actuated motor is used to detect the rotational angle of the frame body. The rotor is made of aluminum, and the frame body is made of stainless steel, both with enough sectional area such that the whole architecture can be assumed to be rigid without any deformation. Now this figure on the right shows the finite element subdivision of the experimental setup with each connection to connection modeled with a single Bernoulli Euler beam element. The capabilities of modeling this kind of complex architecture and computing of dynamics are the main features of the parallel solution scheme. A rotational motion of a 4 pi radian in 2 seconds is given to the rotor. The motion torque required for driving the rotor, which is calculated at the upper node of this element number 3, is obtained by the parallel solution scheme as shown in this figure. Reaction moments generated at the exact location of the TCS here are calculated as shown in this figure. To cancel these moments, the perfect same torque should be supplied to the TCS. Now, this is the motion of the overall architecture when the TCS is not activated. And this is the motion when it is activated. If you look at this figure, which shows the rotational angle of the frame body, detected at the encoder attached on this pin joint, you can see that the frame body is unstable during the motion when the TCS is not activated. Whereas the rotation on the pin joint stops perfectly when the TCS is activated. Now this means that the reaction moments generated around the rotating axis are cancelled perfectly by supplying the accurately computed cancelling torques to the TCS. Next, an experiment was carried out on a different configuration of the frame body as shown in these figures. The only difference between the this case and the previous one is that a TCS is mounted in the offset position of the rotating axis. We try to see if such a condition affects the torque cancelling result. The whole system is modeled with a total of 25 elements and 26 nodes as shown in this figure on the right. The same rotational motion is given to this rotor as in the previous experiment. The motion torques for driving the rotor are the values calculated at the upper node of element number 3, and the reaction moments are the values calculated at the upper node of element number 25. Now it can be confirmed from these movies and this figure that also in this case, the mechanical sway on the pin joint is successfully suppressed to a minimum amount by activating the TCS mounted in the offset position. Next, a simple flexible link with a TCS experimental setup as shown in these figures was made to carry out a numerical estimation and some experiments for verification. In this setup, a flexible link is driven by a gearless motor, and the prototype TCS is placed at an offset position from the rotating axis of the active joint. The link system is connected to the ground with a rotation-free passive joint when an encoder is used to detect the rotational angle of the overall body. This flexible link is made of polycarbonate, where the elastic deformation should not be neglected in the inverse dynamics calculation. The whole system is modeled with a total of 4 elements and 5 nodes as shown in this figure. The capabilities of modeling and computing the dynamics main feature of this parameter. A rotational motion of 5 radians 2 seconds is given to this active link. The torque required for the active joint is obtained by the parallel solution scheme as shown in this figure. Reaction moment generated at the exact location of the TCS is calculated as shown in this figure. Please note the vibration of the calculated torques due to the elasticity of the flexible link. By activating the TCS, the mechanical sway around the pin joint is successfully suppressed to a minimum amount in this case too. This figure shows the rotational angle of the link system detected at the encoder attached on the passive joint. It can be confirmed from the figure that the rotation around the passive joint stops perfectly when the TCS is activated by the torque obtained by assuming the elasticity of flexible link. If a torque obtained by assuming it as a rigid link is supplied, you can see that it is not sufficient for the TCS to suppress the mechanical sway around the passive joint. Last of all, the TCS was applied to a walking robot. As you can see, the TCS is mounted at the center of this walking robot, which walks only on metal sheets by taking a grip by electromagnetic field. However, the robot may sway during the motion because of its quite large mass. This is the finite element subdivision, and we calculated the torque required for a 3-step motion and the TCS using the parallel solution scheme. The target spot after steps is shown here. Stability of the motion is increased by activating the TCS, and the average gap between the target and actual landing spots are decreased by about 75%, as you can see in this figure. I would like to summarize my talk. Both methods I've shown today are based upon theories incorporated with beam elements. The YesIGot code incorporated with linear Timoshenko beam elements can practically simulate the collapse behaviors of buildings and motion behaviors of indoor non-structural components. The computation cost is very low, and the most attractive point of this code is that it can be used in any personal computers with smaller memories. The torque cancelling system is developed using the parallel solution scheme of inverse dynamics incorporated with Bernoulli Euler beam elements. I have shown that it can cope with elasticity of link members and can also cope with complexity of link systems by using a finite element approach. But what I wanted mostly to emphasize is that there are still many fields out there where you can apply computational mechanics. Okay. Thank you for your kind attention. Thank you.